Client honeypot. Honeypots are security devices whose value lie in being probed and compromised. Traditional honeypots are servers or devices that expose server services that wait passively to be attacked. Client honeypots are active security devices in search of malicious servers that attack clients. The client honeypot poses as a client and interacts with the server to examine whether an attack has occurred. Often, the focus of client honeypots is on web browsers, but any client that interacts with servers can be part of a client honeypot, for example, FTP, SSH, email, etc. There are several terms that are used to describe client honeypots. Besides client honeypot, which is the generic classification, HoneyClient is the other term that is generally used and accepted. However, there is a subtlety here, as HoneyClient is actually a homograph that could also refer to the first known open-source client honeypot implementation. See below, although this should be clear from the context. Architecture. A client honeypot is composed of three components. The first component, a queuer, is responsible for creating a list of servers for the client to visit. This list can be created, for example, through crawling. The second component is the client itself, which is able to make requests to servers identified by the queuer. After the interaction with the server has taken place, the third component, an analysis engine, is responsible for determining whether an attack. In addition to these components, client honeypots are usually equipped with some sort of containment strategy. This is usually achieved through the use of firewalls and virtual machine sandboxes. Analogous to traditional server honeypots, client honeypots are mainly classified by their interaction level, high or low, which denotes the level of functional interaction the server can utilize on the client honeypot. In addition to this, there are also newly hybrid approaches which denotes the usage of both high and low interaction detection techniques. High interaction client honeypots are fully functional systems comparable to real systems with real clients. As such, no functional limitations besides the containment strategy exist on high interaction client honeypots. Attacks on high interaction client honeypots are detected via inspection of the state of the system. The detection of changes to the client honeypot may indicate the occurrence of an attack against that has exploited a vulnerability of the client. An example of such a change is the presence of a new or altered file. High interaction client honeypots are very effective at detecting unknown attacks on clients. However, the trade-off for this accuracy is a performance hit from the amount of system state that has to be monitored to make an attack assessment. Also, this detection mechanism is prone to various forms of evasion by the exploit. For example, an attack could delay the exploit from immediately triggering time bombs, or could trigger upon a particular set of conditions or actions logic bombs. Since no immediate, detectable state change occurred, the client honeypot is likely to incorrectly classify the server as safe even though it did successfully perform its attack on the client. Finally, if the client honeypots are running in virtual machines, then an exploit may try to detect the presence of the virtual environment and cease from triggering or behave differently. Capture-HPC. Capture-1 is a high-interaction client honeypot developed by researchers at Victoria University of Wellington, NZ. Capture differs from existing client honeypots in various ways. First, it is designed to be fast. State changes are being detected using an event-based model allowing to react to state changes as they occur. Second, Capture is designed to be scalable. A central capture server is able to control numerous clients across a network. Third, Capture is supposed to be a framework that allows to utilize different clients. The initial version of Capture supports Internet Explorer, but the current version supports all major browsers: Internet Explorer, Firefox, Opera, Safari, as well as other HTTP or client applications, such as Office applications and media players. HoneyClient. HoneyClient 2 is a web browser-based, IE/Firefox High Interaction Client Honeypot, designed by Kathy Wang in 2004 and subsequently developed at MITRE. It was the first open-source client honeypot and is a mix of Perl, C++, and Ruby. HoneyClient is state-based and detects attacks on Windows clients by monitoring files, process events, and registry entries. It has integrated the Capture-HPC real-time integrity checker to perform this detection. HoneyClient also contains a crawler, so it can be seeded with a list of initial URL from which to start and can then continue to traverse websites in search of client-side malware. HoneyMonkey, dead since 2010. HoneyMonkey 3 is a web browser-based IE high-interaction client honeypot implemented by Microsoft in 2005. It is not available for download. HoneyMonkey is state-based and detects attacks on clients by monitoring files, registry, and processes. A unique characteristic of HoneyMonkey is its layered approach to interacting with servers in order to identify zero-day exploits. HoneyMonkey initially crawls the web with a vulnerable configuration. Once an attack has been identified, the server is re-examined with a fully patched configuration. If the attack is still detected, one can conclude that the attack utilizes an exploit for which no patch has been publicly released yet and therefore is quite dangerous. SHELIA, dead since 2009. SHELIA 4 is a high-interaction client honeypot developed by Joan Robert Rockespana at Universiteit Amsterdam. It integrates with an email reader and processes each email it receives URL and attachments. Depending on the type of URL or attachment received, it opens a different client application, e.g. browser, Office application, etc. It monitors whether executable instructions are executed in data area of memory, which would indicate a buffer overflow exploit has been triggered. With such an approach, SHELIA is not only able to detect exploits, but is able to actually ward off exploits from triggering. Spycrawler. The Spycrawler 5 developed at the University of Washington is yet another browser-based Mozilla high-interaction client honeypot developed by Maschuk et al. In 2005. This client honeypot is not available for download. The Spycrawler is state-based and detects attacks on clients by monitoring files, processes, registry, and browser crashes. Spycrawler's detection mechanism is event-based. Further, it increases the passage of time of the virtual machine the Spycrawler is operating in to overcome or rather reduce the impact of time bombs. Web Exploit Finder. WEF6 is an implementation of an automatic drive-by-download detection in a virtualized environment, developed by Thomas Muller, Benjamin Mack, and Mehmet Arzaman, 3 students from the Hochschule der Medien HDM, Stuttgart, during the summer term in 2006. WEF can be used as an active HoneyNet with a complete virtualization architecture underneath for rollbacks of compromised virtualized machines. Low interaction. Low-interaction client honeypots differ from high-interaction client honeypots in that they do not utilize an entire real system, but rather use lightweight or simulated clients to interact with the server. In the browser world, they are similar to web crawlers. Responses from servers are examined directly to assess whether an attack has taken place. This could be done, for example, by examining the response for the presence of malicious strings. Low-interaction client honeypots are easier to deploy and operate than high-interaction client honeypots and also perform better. However, they are likely to have a lower detection rate since attacks have to be known to the client honeypot in order for it to detect them. New attacks are likely to go unnoticed. They also suffer from the problem of evasion by exploits, which may be exacerbated due to their simplicity, thus making it easier for an exploit to detect the presence of the client honeypot. HoneyC. HoneyC 7 is a low-interaction client honeypot developed at Victoria University of Wellington by Christian Seifert in 2006. HoneyC is a platform-independent open-source framework written in Ruby. It currently concentrates driving a web browser simulator to interact with servers. Malicious servers are detected by statically examining the web server's response for malicious strings through the usage of snort signatures. HoneySpider dead since 2008. HoneySpider 8 is a low-interaction client honeypot initially developed at the University of Mannheim by YALIH. HoneySpider is a crawler-based client honeypot initially utilizing antivirus solutions to detect malware. It is claimed to be fast and expandable with other detection mechanisms. The work has started as a diploma thesis and is continued and released as free software under the GPL. HoneyC dead since 2015. HoneyC9 is a low-interaction client developed by Jose Nazario. HoneyC mimics legitimate web browsers and can understand dynamic content by deobfuscating malicious content for detection. Furthermore, HoneyC emulates specific vulnerabilities to pinpoint the attack vector. HoneyC is a modular framework that enables the study of malicious HTTP pages and understands modern vulnerabilities and attacker technique. Spyby, 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 Spyby 10 is a low-interaction client honeypot developed by Niels Provos. Spyby allows a webmaster to determine whether a website is malicious by a set of heuristics and scanning of content against the CLAM AV engine. Thug, 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 Thug. Thug 11 is a low-interaction client honeypot developed by Angelo Delira. Thug emulates the behavior of a web browser and is focused on detection of malicious web pages. The tool uses Google Vate JavaScript engine and implements its own document object model DOM. The most important and unique features of Thug are the ActiveX controls handling module vulnerability module and static plus dynamic analysis capabilities using abstract syntax tree and LiMU shellcode analyzer. Thug is written in Python under GNU General Public License. YALIH. YALIH, yet another low-interaction HoneyClient 12, is a low-interaction client honeypot developed by Masood Mansouri from the Untitled Chapter of the Victoria University of Wellington, New Zealand, and designed to detect malicious websites through signature and pattern matching techniques. YALIH has the capability to collect suspicious URL from malicious website databases, Bing API inbox, and spam folder through POP3 and a map protocol. It can perform JavaScript extraction, deobfuscation, and deminification of scripts embedded within a website, and can emulate referrer, browser agents, and handle redirection, cookies, and sessions. Its visitor agent is capable of fetching a website from multiple locations to bypass geolocation and IP cloaking attacks. YALIH can also generate automated signatures to detect variations of an attack. YALIH is available as an open-source project. minic. minic 13 is a low-interaction client honeypot based on wget retriever and Yara engine. It is designed to be light, fast, and suitable for retrieval of a large number of websites. minic allows to set and simulate referrer, user agent, accept language, and few other variables. minic was designed at New Zealand Untitled Chapter of the Victoria University of Wellington. Hybrid client honeypots. Hybrid client honeypots combine both low and high interaction client honeypots to gain from the advantages of both approaches. HoneySpider dead since 2013. The HoneySpider 14 network is a hybrid client honeypot developed as a joint venture between NASC/CERT Polska, GovCERT. The project's goal is to develop a complete client honeypot system based on existing client honeypot solutions and a crawler specially for the bulk processing of URL. Literature. Jan Goebel, Andreas Duld, Client Honeypots, Exploring Malicious Websites, Oldenburg Verlag 2010, ISBN 970-3-486-70526-3. This book at Amazon. Papers: M. Agel, P. Werzinger, C. Krugel, and E. Kurta defending browsers against drive-by downloads, mitigating heap spraying code injection attacks, Secure Systems Lab, 2009, p. Available from iceclub.org, accessed May 15, 2009. Feinstein, Ben. Caffeine Monkey Automated Collection, Detection and Analysis of JavaScript. Black Hat USA, Las Vegas, 2007. Ikansai, A. Halls, T. Frailing, F.C. HoneySpider Detecting Malicious Websites with Low Interaction HoneyClients. Sicherheit 2008, 407-421 Archive 2013-1-2 at the Wayback Machine. Moschuk, A. Brajan, P. Gribble, S.D. and Levy, H.M. A crawler-based study of spyware on the web. In 13th Annual Network and Distributed Systems Security Symposium NDSS. San Diego, 2006. The Internet Society. Provost N. Halls, T. Virtual Honeypots, From Botnet Tracking to Intrusion Detection. Addison Wesley, Boston, 2007. Provost N. Mavramatis, P. Abu Rajab M. Monrose, F. All your iframes point to us. Google Technical Report. Google, Inc., 2008. Provost N. McNamed D. Mavramatis, P. Wang K. Matajugu and the Ghost in the Browser, Analysis of Web-Based Malware. Proceedings of the 2007 Hotbots. Cambridge, April 2007. Usenix, Seifert, C. Endicott Popovsky, B. Frank D. Komisarczuk, P. Musavas I.R. and Welch, I. Justifying the Need for Forensically Ready Protocols, a case study of identifying malicious web servers using client honeypots. In 4th Annual IFIP-WG 11.9 International Conference on Digital Forensics, Kyoto, 2008. Seifert, C. Know Your Enemy. Behind the Scenes of Malicious Web Servers. The HoneyNet Project. 2007. Seifert, C. Komisarczuk, P. and Welch, I. Application of Divide and Conquer Algorithm Paradigm to Improve the Detection Speed of High Interaction Client Honeypots. 23rd Annual ACM Symposium on Applied Computing. Ceará, Brazil, 2008. Seifert, C. Steenson, R. Halls, T. UNB Davis, M. A. Know Your Enemy Malicious Web Servers. The HoneyNet Project. 2007. Available at honeynet.org. Seifert, C. Welch, I. and Komisarczuk, P. Honey C. The Low Interaction Client Honeypot. Proceedings of the 2007 NZCSRCS. University of Waikato, Hamilton, New Zealand. April 2007. C. Seifert, V. Dilwadia, P. Komisarczuk, D. Sterling, and I. Welch. Measurement Study on Malicious Web Servers in the NZ domain in 14th Australasian Conference on Information Security and Privacy Assist, Brisbane, 2009. C. Seifert, P. Komisarczuk, and I. Welch. True Positive Cost Curve, a cost-based evaluation method for high-interaction client honeypots in Secureware, Athens, 2009. C. Seifert, P. Komisarczuk, and I. Welch. Identification of malicious web pages with static heuristics in Australasian Telecommunication Networks and Applications Conference, Adelaide, 2008. Sturman, Thijs Verduin, Alex. HoneyClient's Low Interaction Detection Method. Technical Report. University of Amsterdam. February 2008. Wang Y. M. Beck D. Zhang, X. Rosov, R. Verbowski, C. Chen, S. and King, S. Automated Web Patrol with Strider HoneyMonkeys, Finding Websites that Exploit Browser Vulnerabilities. In 13th Annual Network and Distributed Systems Security Symposium NDSS. San Diego, 2006. The Internet Society. Huge Giant Wei, Halls Thorsten, Guo Jinpeng, Han Xinhui Zhu Wei. Studying Malicious Websites and the Underground Economy on the Chinese Web. Proceedings of the 2008 Workshop on the Economics of Information Security. Hanover, June 2008. Presentations. Presentation by WebSense on their HoneyClient infrastructure and the next generation of HoneyClients. They are currently working. April 2008 at Ars Amnis 2008. The HoneyNet project. Bertolt Lamrauten in German. Video of Michael Davis client honeypot presentation at HIT 2006. Video of Kathy Wang's presentation of HoneyClient at Recon 2005. Video of Wolfgarten's presentation at CCC conference. Sites. https://web.archive.org/web/20 100 billion 131 million 222,145/https://projects honeynet.org/capture-HPC https://web.archive.org/web/20 71 billion 204 million 172,932/http://handlers dshield org/rdanford/pub/second generation HoneyClients https://web.archive.org/web/20 100 billion 131 million 222,101/https://projects honeynet.org/honeyc/mike/ https://archive https://web.archive.org/web/20 180 billion 430 million 12,758/http://www honeyspider.net/ http://monkeyspider sourceforge.net/ https://code google.com/p/phonics/nick/phonics/nick/phonics/ https://github.com/buffer/thug http://www.cs.vu nl/Herbert/misc/SHELIA/ http://www.spyby.org/spyby.org/ https://web.archive.org/web/20 70 billion 322 million 205,829/http://www.xnos.org/security/overview HTML https://web.archive.org/web/20 100 billion 220 million 13,531/http://code mw-collect org/collect org/collect org/ http://nzhoneynet.org https://github.com/masoodm/YALIH https://github.com/masoodm/minic